Okay. So let's repeat this. I start with the binomial distribution where n is the number of trials which has been fixed. P is the probability of success in each trial independently of the others. And small x is the number of successes. And B is the PMF, right? Now, and there are certain situations where these um, successes are very rare. So let me use the word rare, right? Now, even if they are not rare, we make them rare by certain assumptions, right? So if we attach time to this, right? So rather than just saying, okay, these are Bernoulli trials, we attach a time axis to this. So we imagine as if these events are happening in time. So then you have a fixed interval of time, and yeah, then in that time events can happen. Now, if we narrow down this time interval, right? So I'm now making it smaller and smaller and smaller. So delta t, and I make this delta t so small that at most only one success is possible. You see, and because of this short time, so either nothing will happen, or if something happens, it will be just one success. So when that happens, then I mean, how do we represent this? So that's why we can use the word rare here. Yeah, you use the English word rare for situations that are not very frequent. Yeah, so it's the opposite of frequent. Rare is the opposite of frequent. So, and the reason is this delta t. So it means that that small p, this small p, I think we should instead of small p we should use some other symbol because we will need p for another purpose here. Let's use theta for that purpose. Yeah. So the success probability we are writing small theta for that. So small theta is very very small. Yeah, because of this small interval. Now, if you can recall something from Riemann integration, you remember this when you were integrating a curve, you had a similar situation. Yeah, you had to break it down into smaller intervals. So if you make this interval really small, what will happen to the number of intervals? Can you recall that?
They become infinite.
Infinite. Yeah. So that's the catch. Yeah. So here, the reason this theta is small is because delta t is small. So what can now you say about n, the number of trials? That
We
number of
tend towards
that would
infinity.
be no. The number of trial is the whole thing. Yeah. The number of, I mean, in binomial you have to fix the number of trials. So that number of trials will be very very small if you compared it to this delta t, because for each for each delta t you have you think of each delta t as a trial, whether that trial is a success or a failure is a separate thing. Yeah, so maybe I have to clarify this. So in each delta t I have a trial, and that trial will either be a success or a failure. So the success is rare, failure is common. So but I am now increasing the number of trials, so it means that n is very very large, right? Similar to a Riemann integral. So what is the product n times theta? Do you recall from the binomial distribution? N times theta. Of course, there it was n times p, but here I am writing n times theta. Can you recall what was the meaning of this quantity for binomial? Hmm? Let me show you here. Okay, I'll not be highlighting it because I can't write on this document, but you will see it now, right? Yeah, can you see this box now? What do you see in the box? The mean and variance. So what is the mean? N times P. What is the variance? N times P times Q. So N times P, which for us is N times theta, is the mean, right? So I can now safely say that this N times theta is the mean mu of the binomial process. So even though one of them is really small, the other is really large, the product is neither small nor large, right? Because you multiply these two and you can still have a finite number. So when that happens, and if you follow this algebra, let's say I write, the formula for binomials looks like something like this: p to x and 1 minus p to n minus x. And in this case, I'm replacing p with theta, right? So theta, and I'm now applying the limit n approaching infinity, theta approaching zero in such a way that n times theta is equal to a fixed number mu. When I allow all of this, yeah, let's say there is some calculus guy who's doing it for me, it will turn out that this distribution, the binomial distribution, has two parameters, n and theta. But if I apply these limits, right, these limits, then I have a new distribution, and that distribution will have just one parameter, mu, because n and theta, they disappear in these limits. Whenever you apply limits, yes, was there any question? Okay, so this binomial distribution boils down to a new distribution which we will call power. And now you will understand why I was not writing p there, because the textbooks, most of the textbooks at this point, they use small p for the PMF of the Poisson. Just like B is for the binomial, small p is for the Poisson. So if a textbook is writing POI instead of P, then they can use P here, yeah, no problem. But because he's using small p here, so we can change that small p to theta or some other thing. We can use any other symbol. Let's get back um, to the textbook. Yeah, and I would highly recommend you to read this section, right? Because here he is just reminding you why negative binomial and geometric distributions are so useful, and in particular this paragraph, because in both negative binomial and geometric you fix the number of fixed successes. So you are looking for a desired number of successes, and then you are asking how many trials do I need that. Now this thing becomes important in some areas, especially I'm now highlighting those things. So so trial can be seen as some attempt in a real world situation. Yeah, you are attempting something. You are attempting, let's say, um, you are investing in some business, or uh, you're taking exams or whatever. Yeah. So, but in some cases these attempts are costly in some sense. Yeah. So either in terms of resources, or in terms of time. So a common example is drilling. Yeah. Let's say you want to drill different locations to find oil or water. Yeah. So the success will be finding water or finding oil at that location, and drilling will be a trial. Yeah. So in this case that these drillings are costly. So if you're looking for a fixed number of successes, yeah, whether which is one or a fixed number in negative binomial, this distribution has practical consequences. You can actually decide whether to go for that. So now we get to this new topic, Poisson distribution, which I just started. And because I started with binomial, and then I told you that in that limiting process where the number small n of trials is infinitely large, and the probability small p or theta of success in each trial is infinitely small. That thing can be described in another way, right? So because of its connection to binomial, you are still looking for the number of occurrences of a certain kind, number of outcomes of a certain kind, which for us is successes. But you are counting it in a given time interval, right? Yeah. So you see, we had those small intervals, and then later on, you count it in that large interval from 0 to t. But 0 to t uh, does not address the issue. Yeah, when you break 0 to t into small intervals and delta t is approaching 0, this is where the limiting process occurs. But later on, just like in integration, right? You although you break it down into small integral intervals, but later on you do integrate. So when you count the number of successes in that interval of time, you get this new distribution, and we call it a Poisson random variable, right? So this x previously was a binomial random variable, and in this limiting process, it will be a Poisson random variable, and this experiment will now be a Poisson experiment, right? Now, the way I explained it to you was as if everything was happening in time, but you can have a similar situation where no time is involved. You are just discovering things in space. Yeah, let's say there is a road, and you don't want to think in terms of time. You just say, okay, there is one speed bump, and then there is another speed bump, and you're just counting speed bumps in a long distance, right? Or in a two-dimensional setup, you have a field, you have a ground, let's say, or a yeah, field, I would say, and in that you are just counting trees. Yeah, I have a tree here, I have a tree here, and trees are occurring randomly in a forest. So whether you have time in mind, whether you have a one-dimensional space in mind, a two-dimensional or a three-dimensional space, or some other domain of interest, as long as you can imagine a binomial distribution with those two limits, n and p, one approaching infinity, the other approaching zero. This strange thing that whenever I click this is the disadvantage of these hyperlinks. Yeah, you click something and it goes there. So you will arrive at a Poisson distribution, right? So the Bernoulli process becomes a Poisson process. And to make sure, yeah, I would highly recommend you to read these things. Yeah, the specific region, specific interval. Yeah, you can either be counting things uh, in an hour, yeah, or during winter. Yeah, so if you say during winter, you are talking about a time interval of 3 months, for example, or 2 months. Um, a baseball season will be a few months or a few weeks. And if you are talking in terms of space, you can have, okay, a line segment, yeah, or an area or a volume or some piece of material. So in all these cases, you are counting events, and each event is a success, and you have those limiting processes. So let's dig further and see how to spot these Poisson processes, because you see that the applications are so wide. Instead of looking for all these applications, let's summarize the salient features which you must be looking. And these three features should remind you of what we saw in Bernoulli process. If you remember Bernoulli process, we had something similar. Yeah, we had events occurring or trials. They were independent, right? And they were identical in some sense, and so on. So the first point, when is a process called a Poisson process? So the number of outcomes occurring in one time interval, this is when you have time. But if you have space, then you have to use a different language, a specified region of space. It can be in one dimension, it can be two dimension, or in three dimensions, and so on. This number is independent of the number that occur in any other disjoint interval or region. In this sense, the Poisson process has no memory, because if it had memory, then these two intervals would have dependence on each other. Yeah. So if I let's say pick one example from the above paragraph and see what do you mean by this has no memory thing. So let's pick the first thing, um, the telephone calls received. So let's say you are counting the number of, so let's say X represents the number of phone calls received in 1 hour in an office, right? So let's say I'm now removing all of this. So okay, so let's say I'm counting it from 8 a.m. in the morning to 9 a.m. in the morning. This is one interval, right? And then I am counting. So let's say count the calls, right? Telephone calls. And now I am counting it from 2 p.m. to 3 p.m. Yeah. So what matters is that this is 1 hour and this is also 1 hour. So the number of calls here and the number of calls here, they are independent of each other. So the probability of distribution doesn't care. If you can link it to signals and systems, yeah, there you simply say that the system has no memory. It doesn't matter when you apply, yeah, your input. Whether you apply it now or whether you apply it 1 hour later, the system will always respond in the same way. So here, of course, you are not dealing with LTI here. You are dealing um, with a process of events, and you are just counting things, yeah, because Poisson process is always about counting. So, but if that count has no memory, then only then you can call it a Poisson process. But this is the first thing you need to keep in mind. And I'll just highlight, instead of highlighting it, I'll just encircle. The first point is about independence, right? And independence should be described in terms of
By
having yes,
by the number of outcomes, we mean the number of successes, right?
yes. We don't want to use the number success here, because success is a language used specifically in binomial, geometric, Poisson. No, binomial, geometric, and negative binomial. Uh, when you apply that limit n and p, somehow the success terminology is gone, right? Um, because success is a discrete thing, and here you have a continuous time. So there the language will change, right? You just call it occurrences. Yeah, so that the language is occurrences. And maybe if you don't want to use the word outcome, you say the number of occurrences. Yeah. And if
Yeah.
I now link this same thing to another example, let's say this time we pick that the speed bumps. Yeah. So I am on a road and I am not looking at it as a time problem, but as a space problem. So I see road as a one-dimensional space. So occurrence in this case will be coming across a speed bump, right? Bump. So the number of bumps, I'm now counting the number of bumps in, let's say, 1 kilometer, right? So what does independence mean here? That in this kilometer and let's say in some other kilometer, the bumps are occurring independently of each other, right? So there is no memory in the process. I hope you get that first point now. So let's get to the second point. The probability that a single outcome, which means success or occurrence, will occur during a very short. Now, here you see in the first point, there was no requirement of being short. You could choose any interval. The focus was only on independence. But here, point two is about short. It has to be very short. And this is what I did on that separate page. If it is time interval or a very small region, it is proportional to the length of the time interval or the size of the region. And it does not depend on the number of outcomes occurring outside this time interval or region. That's very important. Okay, so let's have it on a separate page. So I'll now explain it with two examples: telephone calls and speed bumps, right? So this is in space and that is in time. So now I'm narrowing down the interval. So this interval is really small, right? So let's say delta t is 1 millisecond, right? And in this case, that delta x will be, let's say, 1 millimeter, yeah, of space. So now the number of occurrences, which in this case would be telephone calls, in this short interval is proportional to this delta t. So it means that if it is small, then the number of calls will also be small. If it is large, the number of calls, it makes perfect sense. Yeah? It cannot be independent of that. But it is independent at the same time because this interval is so small. This has to be independent of any other calls. Yeah. Yeah. So it will not depend on any other. Let's check the language carefully. Yeah, it does not depend on the number of occurrences out at this time. So it doesn't matter how many calls were recorded before. That's also a case of no memory, right? So there is no memory in this process. And this, you can also imagine a proportionality constant. Typically, we use a proportionality constant lambda. So lambda times t will be the expected number of calls. Expected number of calls. And remember, mu was the name used for the mean. Expected is average and average is the mean. So you can now easily see that mu for this short interval is lambda times delta t. Lambda is a fixed number. And in this case, because this 1 millimeter or 1 micrometer is so short, the number of speed bumps or the expected number of speed bumps or mu will simply be lambda times delta x. In this case, it is the length. So proportionality, and it doesn't depend on outside. The third point. The third point is actually linked to the second point. The probability that more than one outcome will occur in such short, it's again because of shortness, or in such a small region is negligible. Yeah, because it is so short or so small, the probability that you can have more than one speed bump or more than one call or more than one occurrence is really, really, really small, right? Now, now I want you to recall something else related to this before we move on. Um, we learned two things. Because when this delta t is small, we know that here it can be seen as a single trial, and that single trial will either be a success or a failure. And we say that, okay, the probability of success, if we call it theta, and the probability of failure, which is 1 minus theta, this theta will be um, number one, it will be very small, which means this will be very large. And we also saw that this will be proportional to delta t, this delta t. So I can now imagine that lambda here, lambda is the constant. So it's small not because of lambda, it's small because of delta t, right? Even if lambda is not small, this delta t being small will make this theta small, right? That's very important to understand. But you can recall another property of this single trial, which is a Bernoulli. You can also think of it as a Bernoulli distribution. What was the mean? So what we say is that the probability of occurrence in this short interval, right, is equal to theta, and that is equal to lambda times delta t, and that is small. We are saying all these things. But what was the mean of this Bernoulli? Can you recall the formula for the mean of any distribution? Remember, sigma x, x, and PMF, right? And I told you that in the case of Bernoulli distribution, it has a very simple calculation. The possible values of x for Bernoulli is 1 or 0. 1 is for the success, right? And 0 is for
Failure.
failure. What was the probability of success? PMF, P, right? Which for us is theta, right? And what is the probability of failure? 1 minus.
1 minus theta.
So what do you get at the end? Theta. So theta is not only the probability of success, it is also the
The
mean.
mean.
That is very, very unusual. And this, you won't see this in any other distribution. Mean number of occurrences. So it means that whether you use the word mean or average or probability in that short interval, they will all be the same, right? Okay. So uh, yeah, so why did I discuss this? It was to explain this third point. Now you will understand why this third point is so linked to that. The probability that more than one outcome will occur in such a time is negligible, right? And you can actually imagine this. Let's say, let's zoom in, okay? So I am now imagining one interval. So if I want to have two outcomes here, two, I would say, occurrences rather than just one, yeah? So then I have to break it down into, so I will say that, okay, there is one occurrence here and one occurrence here. And because they're independent, so I will say, okay, um, it will be that lambda times delta t by 2, for example. Let's say this is half. And again, lambda times delta t by 2. And then I have to multiply. Why? Because of independence, right? So what do I get here? Lambda squared delta t squared by 4. And if delta t is small, delta t squared will be extremely small. So that's why it is negligible. It is very similar to calculus. Yeah, in calculus, you when you look for differentiation, you ignore the higher order terms. Yeah, so it is this higher order probabilities that are extremely small. So think of these as the higher order terms in a Taylor series expansion. So if you have understood these 3 points, we can now get straight to the formula. And remember, the mean number of outcomes is lambda times t, right? Um, so that t will either be a specific time, if it is a time problem, if it will either be a distance, if it's a one-dimensional space problem, it could be area, if it's a two-dimensional area problem, it could be volume, if it's a three-dimensional problem, and so on. Yeah. So as I already told you that the binomial semicolon n comma theta, I don't want to confuse this small p here, because that small p is now the PMF, and x, this will be approaching in that limit to a new distribution. And this lambda t, remember, is simply the mu, right? I told the mu because mu is equal to n times p, right? But why do we want to see lambda here? Mu is the mean and it depends on time. So if I have 0 and if I have t, and this t can be, I can make this t as large as I want. So I also need something which is for the small delta t, and that is where lambda becomes useful. Yeah. So I need two quantities. One is lambda and one is mu, and they are related in this way that it is lambda times. If this mu is in a short interval, then it should be lambda times delta t. But if it is open, then it would be lambda times t because lambda is constant. Yeah. So so that's why it becomes more useful. It's very similar to distance and velocity, right? So if you use displacement or distance, and if you use velocity, the advantage of velocity is that you can narrow it down to very short intervals. And distance doesn't tell you anything about time. So if we stick to mu only, then we will have no way of tracking time. But if we use lambda, so think about lambda as mu by t. So let me just bring this t here. And if mu is the mean, this lambda is the rate. Yeah. So I can say it's the mean occurrence number, number of mean occurrences, and this is the rate of occurrences, right? And you will see now when we get to numerical problems, you will see why lambda um, is more useful than mu in some problems. And we are skipping that derivation. So I told you that this nx theta to x 1 minus theta to n minus x in the limit will approach this distribution. So we're just giving the final result without using that calculus thing. You can find it in some advanced textbooks, this derivation. But for us, what is important is that the PMF now depends only on one parameter. You have to see delta times t as a single parameter mu, right? Why am I saying that it's a single parameter where we see lambda times t? So why can't we say lambda and t are two parameters? Any idea? Hmm? It would have been two parameters if it was like this, right? If it was like p x semicolon lambda comma t, this would be two parameters. Once you multiply two things, you get a single quantity, and that is a single parameter. So you can even call it mu if you want, right? So it's a single parameter. And the possible values are 0, 1, 2, and so on. Can you recall the possible values of binomial distribution when this was binomial? What was the possible values? It started with 0, 1, 2, and where did it end? Hmm? The last value was n, right? N was the number of trials, maximum trial, number of trials allowed. So, no, the maximum number of successes allowed. But here n is infinity, n is approaching infinity. So that's why in the Poisson distribution, there is no upper limit on x, right? And now let me remind you some symbols. When we were using small b for binomial and small h for hypergeometric, small g for geometric, and b star for negative binomial, right? So these are all the PMFs. PMFs. What was the notation for CDF? This small b was replaced by capital B, small h was replaced by capital H for hypergeometric, this capital G for geometric, and capital B star for negative binomial. So now if we use small p for Poisson, right? PMF of possum. So for the CDF, you can easily use capital P, right? So it will be capital P, and that lambda t is the parameter which you can call mu, and yeah, you can now use R or X. How do you avoid confusion with simply P? I mean, we use P for probability as well, right? We say, okay, P of X. Can you show me the question in terms of X for this? It will be X what? And let me write R here. So what should I write in between? Hmm? I'm telling you that this is CDF, right? So what question should I write for CDF? Random variable, taking values. What should I write? Equal, greater, less. You recall that? Hmm? You forgot the formula for CDF? Hmm?
Less than,
Less than or
equal to.
equal to, right? And this R is the reason I mean, because the dummy variable is X, so that's why you have to write R here. If you want to write X here and you want to write X here, then you would have to write X there, and then you would have to use a dummy variable here. Yeah, maybe K. So you can do that as well. Yeah, just make that K and then you can write X here. Because he doesn't want to change the dummy variable, so he's using R instead of X, right? So that shouldn't confuse you. Now my question is, how can we live with this P and this P? This P is simply probability. This is not a probability. What is this capital P? Hmm?
The sum.
Yeah. So this thing is the probability, right? At the end, you do get a probability, but P itself is a function, and that function is the CDF. Now, this P is not the CDF. So how do you distinguish between this P and that P? I told you the simple thing in math is to look for the type. What is the type of input here? What do you input to capital P here? Hmm? Is this an event or is this a number? Hmm? Yeah. So when I write this thing, I'm highlighting this. This thing you are inputting is not a number. It is a subset. Yeah? It is an event. But here you are inputting a number. Actually, you are inputting two numbers. Yeah. After the semicolon, you also put a number. So you can imagine a computer program which checks the input type. Yeah. So when it finds that okay, you can think of it as the operator overloading, right? The operator overloading. So when the input type is numbers, two numbers, this P will be interpreted as a CDF. But if the input type is an event, which is a subset, then this same P will simply be the probability function, right? And this is obvious, yeah, using the sum. So now we need to get to the tables because we want to be able to use table A.2. So let's go to 750 now. And this is just a reminder because we have been using the binomial CDF. Remember, another way of writing this was capital B, right? And this R was here, the first argument, semicolon, and N and P are the two parameters. N was giving us the block, Small p was giving us the column, right? And this small r was the correct row. So now we need to see how the Poisson table is arranged. Yeah, table A.2. So this is now our CDF. The CDF P, that small r is appear as the first input, and after the semicolon we are using mu. Uh, you can imagine this mu to be lambda times t, but lambda times t can confuse many people. They wouldn't know lambda, they wouldn't know t. So what you should do, whatever the value of lambda is, whatever the value of t is, multiply the two. This t will either be time or space, yeah, or length or distance or area or volume. And when you do this multiplication, you convert it into a single number mu, and that mu is your parameter. Because in the table of Poisson CDF, you are not going to find lambda or t. You're only going to find mu, right? So this will be the correct column, right? And R will be the correct row, right? Keep this in mind now. So now we are going to apply these concepts to our first example. You are going to do actually three things. First, you have to establish why this is a Poisson experiment. You have to justify that by reasoning. Once you do that, then you have to say, okay, what is mu, what is lambda, what is t, right? You either find mu directly or you find lambda and t and then find mu. And after that, you can use this table or you can use the formula, right? Okay, so let's apply this to the first example. Yes. So if you can remember these 3 points, right? These 3 points. The first was about independence. The second was about the interval being so short that only one outcome or one occurrence or one success is a possibility, and the probability of that happening is very small. And the third point makes sure that more than two outcomes are nearly impossible, right? So if you can recall that, then tell me, why should I trust that this problem is a Poisson problem? During a lab experiment, the average number of radioactive particles, you should recall radioactivity from physics or chemistry, passing through a counter. So you have a counter which is counting radioactive particles passing. So the radioactive particles can only come from from a radioactive element, right? And you are doing it in 1 millisecond. And the average number recorded in that 1 millisecond is 4. What is the probability that 6 particles enter the counter in a given millisecond? So why is this a Poisson process or a Poisson experiment? Hmm?
Because we're confined to a single millisecond.
That is one reason. The other reason, that will not address the first point, yeah, that addresses the second and third point. We are counting, right? We are counting the number of occurrences, yeah. What does the first point say?
Because, yeah,
The number of and one time interval and independence. It is independent from one interval to the next. So you see, imagine a radioactive element, the number of particles emitting it and being recorded at the counter will not depend on what happened in the previous hour or the previous minute, right? And they are happening in time, right? So they will either be happening in time or in space. In this case, because it's a counter, so you are counting, so it will be happening in time. So you need to make sure that Poisson process is a good model, right? Now, next thing, where how do we identify mu or lambda, right? And make sure that you know this, that lambda is the rate of occurrence, t is the time or space region, and mu is the average. And mu equals lambda t. This is important. Mu equals lambda t. So how should I interpret the first thing? The average number of radioactive particles passing through a counter in 1 millisecond is 4. Is this 4?
Mu.
It is mu. There is a trick. There is a trick in this. This formulation is only safe if this 1 millisecond is fixed in the question. In this question, he is again asking the question a given millisecond. So because time is fixed, the value of t is fixed. So it doesn't matter whether you use mu or lambda, right? Why?
Yeah.
Because we can define t to be the number of, remember, I told you not to attach units in this course. It is very dangerous. So let's say we use t to be the number of milliseconds. Yeah? Number of milliseconds. It's a number now. Now, what is the value of t in this problem? 1.
1.
So when t is 1, then mu is equal to lambda times t, and lambda is also 4. Yeah, because of, so it's because of the simplicity that you can call it mu. But I will not change the question, and then you will see that mu will not be a good idea. So let's solve this question as it is. What is the probability that 6 particles enter the counter in a given? So we need to frame this now in terms of this first. First, let's frame it in terms of this. So it will be, now you're going to tell me, small p of what? Use this notation. What is the value of small x? Hmm? Small x is the value of capital X. Capital X is the number of occurrences.
Yeah.
So 6. So it is, small x is 6. Then semicolon. What should I write after the semicolon?
4.
4. Why? Because lambda times t is 4. Now, one way of solving this is to use the formula. So first, let me see how to write the formula. So it will be exponential minus what?
-4.
Minus 4, because lambda times t is 4, right? Okay. 4 is lambda times t, and that is mu. Then in the bracket,
4
4,
to the 6th power.
4 to the 6, and there is 6 factorial. Yes. Let's say you want to do it with the table and you don't want to use calculator. So then express this in terms of the CDF. So CDF minus CDF, semicolon, semicolon 4, semicolon 4. Now tell me, what should go here? You have seen this example where you can express any probability in terms of CDFs. This is capital P, right? This is small p. This is capital P, CDF. What should I write here? Hmm? You forgot this formula?
6 and 5.
6 and 5, yeah. So this will be 6 and this will be 1 before, which is 5. So now we need to look at that table. Mu will be 4 and we'll be looking at two rows, 5 and 6. So it's too much. So mu is 4, right? So we are looking in this column. And which two rows? 5 and 6. So
So
we, huh?
how do these tables apply generally to everything? Like how did they derive these for every Poisson distribution?
No, I didn't hear. Can you say it again?
I'm asking how do they generalize these tables or like derive the tables so that they work for every Poisson distribution?
No, I
Is
mean,
it from the formula or something?
no, but you saw the formula, and instead of using your calculator, they must have written a program, right? And you just run some for loop, yeah. So yeah, I mean, to generate this table is easy. The reason we are using this table is to understand, yeah. If you give everything to a program, then you don't know what is happening, right? So because you have a formula and there are parameters, and for each parameter you should be able to use the formula. So you will subtract this value from this value, right? So this is plus, this is minus, and that should give you the result. I think we have done this for binomial as well. It's nothing new. So let's change the question because this was the easy version. We now need to change the question. Hmm, oh, every time I forget the thing. 150, right? 155. Yes.
So also for every trial is delta t always the same in length?
Huh? Say it again, please.
For every trial is delta t always the same in length?
No, delta t has to be really small. Yeah, but delta t disappears from these calculations if you think about it.
Yeah, but let's say for the previous example we did, we had 1 millisecond.
Yeah, yeah. So
So is
one
it
millisecond. Yeah. Now I'm changing the question, and you will see. You will see that I'll get to that. Okay.
okay?
Um, no, the funny part is no. What is the page number of 180? Okay, 180. So I was using the wrong. Yeah, this should be correct now. We need to get to that point now. Okay. Okay. So now I'm removing this lambda and t and everything. Okay. Let's change this last part. Instead of given millisecond, let's replace this with 3 milliseconds. So now what will you do? What is lambda and what is mu in this case? So here is the importance of understanding the symbols. Yeah, lambda is actually the rate. So lambda will always have the same meaning. Mu depends on time, right? So here I have changed this to 3 milliseconds. So the definition of mu will change, but the definition of lambda cannot change because it's always per unit time. Yeah. So because it is 1 millisecond, so lambda will still be equal to 4, right? Why? Because this is 1 millisecond. But what is mu this time? Mu is not equal to 4 now.
It's 3 times 4.
Yeah, it will be lambda times t, right? So 4 times 3, 12, right? And now let me complicate this even further. I'll now complicate it, which will really test your understanding. So let's say I change this to 2 to, let's say I change this to 3 milliseconds, and I change this to 2 milliseconds. Now what should I do? Now what is lambda?
So lambda will be 2.
Yeah, so you must not forget that lambda is actually the rate of arrivals, the rate of occurrences. So 4 is not the rate now, 4 divided by 2 is lambda. Yeah, and Mu will always depend on the question, right? Right? Because lambda times t is the mu. So it will be 2 times 3, 6. That's what you need to keep in mind. I can even leave this as it is. Let's say I leave this as a given millisecond. So what should I do now? So that is 2 millisecond and I don't change the last line. So what should I do here now? 2 times what? Hmm?
One.
Yeah, because t is still 1, right?
Yeah.
Okay, let's get to this second um, question. So 10 is the average number of oil tankers arriving each day at a certain port. So is it mu or is it lambda? Hmm? What is the safest thing you can say? Let's say you don't read the question, you only read this part. Regardless of what is being asked later on, because this is each day, right? So if you define t as the number of days, right? Number of days, this is automatically per day, and this 10 is the value of
Lambda.
lambda. That is the advantage of understanding it. But of course, if I now change this to the number of, for example, months, then lambda will not be 10. Yeah? Let's say I change it to the number of weeks. So let's say t is the number of weeks. What is lambda? 10 by what?
7.
Hmm? 10 by what? You have to see, it's a rate. So here you have to write the number of weeks in that day. How many weeks do you have in that day? 1/7, right?
That would be 10 times 7.
Yeah. So understanding the meaning of lambda is very important, yeah. And how you define t is also important. And I can change the question for you, and then you will be forced to do it like that, right?
So for the whole time axis, lambda doesn't change, right? It stays the same.
Yes, yes. It depends on how you define your symbol t, right?
Yeah.
You see, for doing this, we don't need to read the question, right? I just have to change what I mean by small t. And depending on how I define small t, the value of lambda will change accordingly. This is actually one of the disadvantages. Remember, there are two approaches. Yeah, I told you that in physics and chemistry, you have to stick to units. Each symbol must carry the units. So that has an advantage that you don't care about the units. Every symbol will carry the units, but the math becomes difficult, right? You have to follow the units in every computation. So in probability and signal systems, we forget about units, but then we have to define our symbols every time differently. So there is a catch, yeah. So lambda is now 10, assuming that t is actually time in days. Time in days. Now let's follow it all. The facility at the port can handle at most 15 tankers per day, right? So it cannot handle more than 15. What is the probability that on a given day tankers have to be turned away? So what will be my definition for x here? X will be the number of, tell me, number of what? Remember, x is the random variable, yeah? It's not a fixed thing. So it will be the number of tankers, right? Arriving, yeah? Read the problem. arriving, the number of oil tankers arriving on a given day or in a given day. In any given day, the number of oil tankers arriving is the random variable. So now tell me which probability is being asked to compute here. P of, tell me, X what? Of course, it has to relate to 15, right? So is it less than 15 or greater than 15?
Greater than.
Yeah, because in that case, it has to be turned away, right? So now, how do I make sure that I use the table? The table is not in that form, right? So I need to change this to the complement, and that is P of X less than or equal to, tell me, what is the complement of this? Hmm?
14.
14, right? 14, but that is the complement, so I have to subtract that from 1, right? And now tell me, 1 minus, now I'm using the CDF, so semicolon. What should I write after the semicolon? This P is now the CDF, right? Pass on CDF.
Yeah.
So what do I write after the column?
14.
After the semicolon, lambda T, right? What is lambda? 10.
10.
What is T?
1.
Yeah, given day, so 1.
So it will be 10.
So it will be 10. And what should I write here?
14 and
14.
13.
14. No, here I don't need 14 and 13. Here I just need to write 14. Why? Because this is already the
So
CDF.
it's already the CDF, yeah.
So do not mix it with the previous question, right?
Mm.
So let's see if we can quickly find it. 1 minus P, CDF at 14 and 10. So what was this? 750, 14 and 10. So mu, mu 10, right? Here we got it. And now tell me which row? 14. And this is my CDF, and I have to subtract this CDF from 1. That is my answer. P of X greater than 15, right?
So we'll be given these tables in the exam paper, right?
Yes, if I want you to use the table, right? So let's change the question here. Let's make it complicated, right? So let's say that I change this given day to 1 hour. So how will the question change now? I don't change anything else. So what will be the value of t? Hmm? You know that depends on when you write lambda is equal to 10. What was the assumption?
That it was
That t was in days.
day.
And if you don't pay attention to that, then you don't know what you're doing. And I am now asking for an hour. So I cannot say t is equal to 1 because it's 1 hour. No, t has to be in days. So hour is not a day.
So 10 by 24.
Yeah, t has to be 1 divided by 24, right? This is the disadvantage of not using units with the symbols. But yeah, that's the only thing you can do in math, right?
Yeah.
Let's complicate this even further. Let's say this is each, uh, let's say this is each week, right? Yeah, this is each week. So now, what will be lambda? And let's not change this. So now I have two options, right? I either have to change my definition of t, so t will be in weeks, right? If t is in weeks, then I don't need to change the value of lambda. Yeah, it will still be 10, right? Because I'm now matching the question. And
Because
then t
still asking for the number for
and
a given
then
year.
yeah, and then 10 will be 1 over 7, right? Right?
Yeah.
And what is the alternative? Let's say that instead of days, I define t to be in weeks. No, sorry. Instead of weeks, I define t to be in days. Then what is the value of lambda? This is still each week, but I define t in days. So it will be,
70.
so it will be 70, and t will be 1, right?
1.
Yes, ultimately, your final computation will not change, but lambda and t have to be written correctly. Yeah. So mu equals lambda times t. It will always be the same, right? There is something very interesting about the Poisson distribution, and that is something you can try at home. Both the mean and the variance are the same, and they are equal to lambda times t, right? And instead of proving it, let me justify it in a more engineering way, right? Because engineers, they try to avoid mathematical proofs. So we know that Poisson is an approximation of binomial, right? So what was the mean and variance for the binomial? It was n times p, and it was n times p times 1 minus p, right? And that p is not to be confused with this p, so I can even write theta there, if in case you get confused, right? So now n is approaching infinity, theta is approaching zero. The product is simply mu, but mu we already know is lambda times t. Yeah, so lambda times t. Now how about this? When theta is approaching zero, 1 minus theta is approaching 1, right? So it's again, yeah. So for Poisson, the variance and the mean are both the same. This is so important that people use this to check whether time series data is following a Poisson distribution or not. Because from the time series, imagine I give you a time series, right? This is time, and these are the values of x. From this time series, think of it as a statistical problem, right? Just like in chapter 1. From this table, you can calculate the sample mean and the sample variance, right? Can you do that? Yeah, it's very easy. I give you a table and I ask you to calculate the sample mean and the sample variance. And now you divide that sample mean, no, that sample variance by the sample mean. This ratio should give you some hint of whether Poisson distribution is the correct model or is the reasonable model. So this ratio should be close to what?
One.
1. So even if it is not exactly 1, you can have an empirical, yeah, argument. Oh, this looks like Poisson.
So how did you write 1 minus theta as 1 for variance?
Because you know that limit, I'm applying that limit, yeah. Limit n approaching infinity, theta approaching 0.
Okay.
Yeah. And actually, to be honest, you should do it in this way, yeah. So it will be n times theta times 1 minus n times theta squared, yeah. And when theta is small, the square is negligible, right? So yeah, that will be a proper way of doing it in calculus. We still have some time for questions. We're done with the topic now. One thing which I want you to connect here is, yeah, I think I told this in the other lecture, so you guys should also know it. Imagine that, remember, capital X for us is the Poisson, yeah, variable. So it's the number of occurrences, right? N time t, n time t. In other words, you imagine an interval 0 to t, right? In this interval. And small x is a particular value, a particular value. And then you have this distribution. Now, let's say there is no randomness. Assume that there is no randomness, no uncertainty. So then we should not use x. We can use simply small x. Small x can be a variable for the number of occurrences. And if lambda is the rate of occurrence, then try to link this quantity. What will be dx by dt? It will be the rate of occurrences, yeah?
Yeah.
And here,
So lambda.
yes, lambda. But here is a catch, you know? The catch is that this is only for small, um, yeah, I think it's correct. You got it right. It has to be lambda. Uh, because this is also small and this is also small, right? So if you now solve this equation, what will be x? X will be equal to,
Theta. Um.
no, just solve this equation. Integrate both sides. So it will be lambda times
Yeah.
t, right? But we already know this. Mu is equal to lambda times t, right? So what does this tell you? What this tell you is that whenever you are using differential equations to model a problem, the claim you are making about that is actually the mean. It's actually the mean. Let me give you an example. We use differential equations in many engineering problems, but what we are actually doing is the mean, because the actual story is much more complicated. So let's say that I write mm, yeah um,
So the variable we're using is usually the mean in differential equations.
yeah, in differential equation you are using actually a variable, and you are even writing differential equations, but um, you are just pretending that it is a deterministic quantity. The underlying quantity is always random, and all you are doing is to follow the mean. Yeah. So if I'm, for example, if I just write this thing, yeah, v equals ir, for example, yeah, there are two variables, I and v, and let's say r is fixed, right? So Ah, yeah. Okay. So you can okay. You say this is sorry वो बंद किया था मैंने. So if we follow this line, right? Uh, this is actually the mean line. So the actual thing will be much more, yeah, random. So you need to write down your attendance in the chat window now, okay? Because I'm closing the session in a while.
So is there any way to